There we go. So like Wojtek said, today we're going to have a closer look on how to monitor regression models in production. And the agenda for today is like, we're going to zoom in silent model failure, what it is exactly, and how it's different from regular machine learning model failure. We're going to talk about the components of a monitoring system. I'm going to show a quick Jupyter notebook with some codes of how you can actually monitor a machine learning model live. And then the common modes of failure that we have seen over the past 2 years, monitoring a lot of machine learning models in production. And then at the end, I'll also quickly demonstrate how you can deploy NannyML itself in production, integrated inside of your production environment. That's going to be a small demo using Docker, Grafana, and Postgres. And that's it for the agenda. So let's go straight into it. Let's first discuss silent model failure, setting the stage a little bit. There's two types of ways a machine learning model can fail. The machine learning model can fail to make predictions, and the model's predictions can fail. And when the model fails to make predictions, we're typically talking about bugs in the code, errors, like the example there, if we provide data in the wrong format, or our resources aren't properly managed, or there is something wrong with the business process itself. And this is typically errors that we can capture with proper software engineering and application monitoring. And then the machine learning model itself can also fail, the predictions meaning. And this just means that when we predict a certain value in the case of regression, that that the error or the difference with the target is growing over time, or it's growing bigger, and that our models become less accurate over time. And the interesting thing about the model's predictions failing is that this failure is kind of silent in the way that because models are decision-making systems, they're supposed to make mistakes. And to distinguish mistakes that are bound to happen by design and real mistakes, because there's something going on deeper or something more profound, is a very hard thing to do. And that is exactly what our open source library focuses on detecting this silent model failure. And there is in general two causes of why a machine learning model can fail silently. One is covariate shift, and the other one is concept drift. And with covariate shift, we typically mean the distributions of the model input changing over time. So if you look at a quick distribution here on which type of people the model was being trained on, we can take, for instance, the example of customer lifetime value estimation, where we try to predict how much value a customer is going to bring to a certain company. And then we can train this machine learning model, and we see that there is mostly young people that we've seen in the past or that have been using the service or the product. And that when we deploy the machine learning model in production, that then there's also older people becoming present, and the machine learning model has to predict on a new type of population, which it wasn't necessarily optimized for during training, and hence prone to making mistakes. And that's the first part. So changes in the distributions of the model inputs over time, and specifically production, comparing it to training or testing. And the other one is concept drift detection, and that is when the relationship between the model inputs and the target changes over time. So if we go again with comparing training and production, we could see that here during training, the younger customers actually had a higher customer lifetime value than when we enter production after a while, of course. And this typically means that the concept or the patterns that the models extracted during training, that they're not going to be very relevant in production anymore. That makes slightly different because of the underlying changes that are happening and our model not being updated or properly refactored or re-engineered. And these two types of issues can cause our machine learning performance to deteriorate and our models to fail silently. And there is another important dimension to this, which is the availability of ground truth. In some machine learning use cases, the ground truth is instantly available. And a way to what we then can do is we can compare the target with the model output and measure some type of error or loss. And this is an example of a classification model, but for regression models, it's exactly the same, where we look at a performance metric during the reference periods, This is ideally testing. And then we deploy the machine learning models, and we can look at the performance metric over time. And typically, these performance data points are created by aggregating data, hourly, daily, monthly, yearly. And then we can see how the performance changes over time. And if the performance drops under a certain threshold, or for regression models, when the loss grows over a certain point and the aggregated error becomes larger, it's then that we will throw an alert and that we will have to delve in deeper and do some investigation of why our models are less performant. And a typical example in a regression use case where ground truth is instant is, for instance, if we're or almost instant, if we're predicting expected time of arrival of cars or planes, then a few hours later, we will know how far off we will be, and we will have gotten the actual target or ground truth. Also, if a customer is on our platform, they're doing certain action, we can then try to predict how much they are going to spend. That is also something that after the customer has spent a little bit of time, we know instantly how much they have spent if they do a checkout, and we can compare and we can have clear view on the performance. Now, in many use cases, the ground truth or the actual outcome is delayed, and it takes a while before the outcome actually comes in. And that creates this problem that we can't calculate the performance during that period. For instance, if we do demand forecasting over a certain window, we want to predict the amount of a call center, or we want to predict energy demand for customers for the coming 3 months. We only really know at the end of that window what the actual demand was. And we need, of course, the demand to compare it with the model output to get some type of performance measure. And what we will then have if we start measuring performance is that at inference time, when the model makes the predictions, we can only see the performance of the model, how the model was doing like a few months ago. And that is, of course, problematic because if we don't have a view on the performance, we can't also really know whether our machine learning models are still making the right decisions. And then there's a third case where the ground truth is completely absent. And this typically happens in automation use cases. We can think insurance pricing. I see that Mike raised his hand. By the way, Mike, you can just drop your questions in the Q&A, and then Wojtek will answer them as we go along with this presentation in the chat. And at the end, there is like 15 minutes left, 20 minutes, where we will pick out some questions and have a discussion about it. Same for you, Gilio. You can just put your questions in the Q&A chat box. But for instance, if we do automation use cases and we do insurance pricing, and imagine that certain insurances used to be priced by an analyst, and that today we replace these analysts by an algorithm that mimics their behavior so that these analysts can focus on more important things, then this algorithm actually removes the process of what was used to be price setting. And then there's no ground truth generated anymore, and we have no view on performance at all. And what we will see here is that at the target, when we go into analysis, that there is no ground truth generated, and we're completely in the dark when it comes to the performance of our machine learning models. So again, in summary, there is two issues that cause silent model failure, which is covariate shift and concept drift. Both can also interact with each other. And then there's this type of third dimension, which makes it hard to monitor machine learning models, and that is the availability of the ground truth. Now, if we go and look at the monitoring system and its components and which parts need to be there to speak of a monitoring system, we first have to establish that a machine learning model is always embedded in a business process and part of a bigger system. And that means if typically our machine learning model is hosted as an API or a prediction service, what will go in is like model inputs, we'll make some predictions, and then later there is actions being taken on these predictions. And if we take the example of the customer lifetime value prediction, we will probably send some information about the customer, maybe what their age is, how much they've spent already, what type of products they have. And if we send that to our prediction service, we will get back what their estimated customer lifetime value is. And based on that, we're going to do different things inside of our platform. Maybe we can do some lead prioritization or maybe some promotions. And as we do those things, we will gather also more information about these customers. Like, for instance, also what their actual customer lifetime value ended up being, the ground truth, if that's available, but also potentially some business KPIs. We can look at the effectiveness of the campaigns. We can see the behavior of these type of customers, maybe segment them as well and see how they're behaving and analyze them a little bit further. And this is also ideally information that we capture and feed to our monitoring system. So we are gonna give this model input, this model output, and this extra data inside of our system. We do a little bit of configuration because every machine learning use case is different based on the business context, based on whether it's streaming, whether it's batch. And these are all things that are very important, and so that we can kind of tailor our monitoring system to a specific use case. Maybe we're interested in different metrics. We're probably also interested in a different granularity of seeing and aggregating data. And also our stakeholders and our model owners, they are going to be different. And that is also something to bear in mind. Hence, there is not really like a monitoring solution that fits all use cases. You'll have to tweak the solution with regards to your specific use case. That's very important. Inside of this monitoring system, there's a few components working together. First of all, it's the logging or the collecting of the data, which is what basically goes into your machine learning model and what we capture later. This data, of course, has to be leveraged by some type of analytics engine. We use NannyML as our backend to do concept drift detection, data drift detection, performance estimation, performance calculation. And all of these analytics have to be working together. And then when there is some alerts, we would love to get notified, of course, so we can get a Slack notification, maybe an email, and that will send us then again to a dashboarding tool or something more visual where we can drill down and come up with a plausible root cause analysis of why our machine learning models are not as performant as they used to be. And of course, it's not just data scientists that are potentially interested in this, but also model owners and business stakeholders as well, because at the end of the day, AI is generating a lot of value. And if we can show that due to people using it, then monitoring will build a lot of trust across the organization. For the demo purposes, we're gonna zoom into a little bit of the analytics part, which is done by the open source NannyML library. And the customer lifetime value prediction use case that I just illustrated a little bit, if we look at which data we would capture over time, is that we have the reference data. This is ideally the test set, where we collect some features about it over time. We know the predictions, and of course, also the ground truth, because this is historical data used to test the machine learning model. And then at some point, we deploy the machine learning model, and then we speak of the analysis period that the model spent in production. And we gather the same information, but the ground truth is not going to be available for all instances. And I'm quickly gonna switch screens here and go to the demo. We prepared a little bit of data for this specific demo, but there's also inside of the NannyML library a lot of data that you can load yourself to try it out, and I highly encourage to pip install and go have a look yourself. So this is basically the data I described. We have a bunch of features, and then again, predictions and the target. And if we go and look at the analysis data, the data of the model in production, we are missing, of course, the target, which we would normally use to compare both and get a notion of the performance. So the first thing we're going to do in our monitoring flow, and this is really what we preach and what we're all about, is to obsess over performance. And this is both machine learning performance from a technical point of view, but also the business performance and the business impact. And in this use case, we're mainly focusing on the technical performance, but this business performance is always something to bear in mind as well. And what we're going to do is we're going to quickly get our features. And then when we instantiate our performance estimation algorithm, in this case, it's because it's regression, we use direct loss estimation. And all of our estimation algorithms and detection algorithms kind of work the same, where when we instantiate, we do some type of mapping between what type of data this algorithm has to see to kind of come up with the conclusion, and with how things are named in the data set. So we have the target, the prediction, which columns are the features, We also decide on which granularity we want to chunk the data. Do we want it on a day, a month, an hour? What column contains the time dimension and which metrics that we're interested in. Specifically for this algorithm, for the direct loss estimation, we also can specify whether we want this algorithm to be very much hyper-tuned and specifically working on this use case. What we do then is then fit this algorithm on the reference period, and it's going to look for a lot of patterns, and then we can kind of use these patterns to estimate the performance on the analysis. I'm just quickly going to run this, and then we can also visualize and get an idea of how our performance, how our machine learning model is doing without having access to the target. Remember, this data frame did not contain a target, and what we do with direct loss estimation is that we leverage the test data, and we basically calculate the loss using the prediction and the target present in test data. And then we train a new machine learning model predicting the loss directly. We're not calculating the error. A small difference here, because error would be just subtracting prediction from the customer lifetime value in this case, but we're also squaring it like how it's typically done in the machine learning metrics, or taking an absolute value so that the measurements are not signed, and that makes it also easier to predict. So basically what this is doing, this is training a machine learning model using the test data, so that then in production, we can, based on what we feed to this machine learning that we train here, we can get an estimate of how the model is most likely gonna perform. And again, based on the test set, we set some thresholds, and when our performance, when the error exceeds, actually in this case, the loss exceeds a certain threshold, we as data scientists are gonna be alarmed because our models are not performing as they used to be, and we'll have to delve in deeper and come up with a plausible root cause. One thing that we should then do as part of this diagnostics is to run multivariate covariance shift. And this is also a custom algorithm inside of the NannyML lab. It kind of works the same. It's called data reconstruction drift calculator. And it's the same thing. We do some type of mapping towards the data. When it instantiates, we fit in the reference, and then we make calculation on the analysis period. And how this algorithm works, it looks at the reference period, and it trains a PCA object that does some decompression and then compresses the data again. And then this compressed data is basically a new type of data set that went to this transformation, and we can compare it and we can measure error. And if when we move into production, the data that we feed it in production is different, then this compression and this decompression, which hasn't changed and which is based on the reference period, is gonna make and transform the data in such a way that this new data set that we create in that way is different, and this reconstruction error is gonna go up. And that is the main sign for a multivariate data drift. And this also captures relationship linear between the different features inside of the input space. And we can also see that in this period, there is some multivariate data drift happening. And after we have established that, we can delve in deeper and go at univariate feature level. Same thing again, we have a univariate drift calculator where we can set some statistics, set some distance metrics that we can use out of the box to calculate univariate feature drift. And then we can do the same thing and visualize some of the features that have drifted over time. And this is specifically for us to go and look at a feature level, and probably need some expert knowledge, or maybe sit down with somebody that has a deep business understanding to piece together why our machine learning models are failing. And for instance, here we can see that our spending actually inside of our application goes up, and specifically the lower the threshold of customers not spending that much is not that much present in these last months. So that is an observation that we'll have to take in, and we'll have to sit down and discuss why this actually might have happened. Then we see something curious here, which is the data plan usage, because distributions haven't changed that much yet. We see some alerts here in these two periods, and this is also a period where there was clearly no drop in performance. And this is something that is bound to happen if we use statistical tests, because these statistical tests are very sensitive in the sense that we have a lot of features in our data set. We apply these statistical tests over time. We can apply some correction like Bonferroni or something that should incorporate some of this repeating of tests and make it a little bit more robust. But unfortunately, these are not the best methods in that sense. And what this will create is a lot of false alarms. And that is exactly what we're seeing here. Because technically, as data scientists, we don't want to be notified when a feature like this drifted and our performance is not impacted. Of course, for a data engineer or from a data quality perspective, this can hold valuable information. But from a performance perspective, if everything is still working, that is not something that we would want to go and investigate. So that is also really why we obsess over performance first and kind of follow this flow of performance and then drilling down and then only using covariate shift detection as a way to come up with an explanation and not as a standalone detection system, because you will just get too much false alarms, and you can already filter out these false alarms by just focusing on the period that there was actually a drop in performance estimated. And then we can see that there's also some other features changing, like we can see some changes on the contract duration going up. And again, a false alarm. And also for categoric features, we can apply the same logic. Here we see that in this last few months, this product type is not present anymore. And maybe that is the type of product that is also related with the lower amount of spending on the platform. And that is something to be investigated. And now it's up to us to put everything together and to basically go and decide what the next steps are. And maybe based on what our automated alerts are, we can trigger continuous retraining. If not, we might want to take the use case down, refactor it, look into deeper, look at the business process, rebuild the machine learning model, or fall back on a previous model. A lot of things of next steps that we can do. But if we understand why our model is not performing, we're going to be able to take better decisions of why these things or how these things can be resolved. And that is it for the monitoring flow. If you have any questions, be sure to put them in the chat, and then after presentation in 20 minutes, we can quickly discuss them. Later, of course, when the time window has passed and the targets become available, we can also, of course, measure the real performance. We can also see that during these 3 months, there was an actual drop in performance, but we would only really know this after a longer time. So this is one of the advantages of estimating performance, is that you don't have to wait for the ground truth and you can act instantly. And we can also look at the model outputs, which is typically something a lot of people already do, and how these distributions change. However, even though model output is in a way also aggregating the feature space into like a single dimension, we're still applying a statistical test. And again, here we see that there is a period when there is actually no drop in performance, and yet the model output distribution has changed a little bit. So not something we need to worry about. But if we wouldn't have an alerting system, which would be just doing a covariate shift, again, we would get a false alarm for this. Inside of our library, we also have different tests. Right now, just visualizing the Kolmogorov-Smirnov test. But I actually also know that Jensen-Shannon is also a little bit more robust to these type of changes. So we could also run this and then potentially not get alerted. And this is also the trade-off of different univariate drift detection metrics. And this can be part of the configuration of your monitoring system, but ideally, these things are also bypassed by focusing on the estimated performance. Quickly gonna go back to the presentation and go into some typical modes of failure, things that we've seen over the past 3 years of how machine learning models fail in production. And The most interesting thing, which I also already touched upon in the demo, is this whole idea that the performance is basically staying constant. There's not that much multivariate data drift, and then there is univariate covariate shift happening, which would induce a false alarm. We'll have to go and delve in deeper, and we get desensitized in the sense that it's not really something that actually ended up being important. And maybe to build some intuitive understanding why certain features, when they drift, they don't impact performance. It's also because today we're pushing the boundaries of our machine learning models. We're including a lot of features inside of them, and not all the features contribute equally to the model performance. And if we have a feature that is not that important, and it shifts a little bit, it might actually that the overall performance it's not that much impacted by. And a way to look at it, from a classification model perspective, is that only covariate shift to uncertain regions is going to impact the performance. So if we look at the training data and we look at the decision boundary, or if we would look at uncertain regions in general, which might be represented close to the decision boundary, or regions where the model actually did not see a lot of data or had a hard time extracting patterns. Maybe it's regions where there is only outliers. If we then move in production and there is more data points appearing in these types of regions where the model is not very certain, where the model is going to make more mistakes, it's only then that our performance is going to be impacted and going to deteriorate. And that's why not all data drift is equal, and we only use it as a way to do some root cause analysis as a first step to identifying what went wrong. And then a typical way, if you have a monitoring system in place, is to look at the estimated performance when it drops. We delve in deeper, we see whether it's covariate shift, and then maybe we can also tie it down to some certain features, and also really come up with a story why the machine learning models have deteriorated and establish the cause so that we can take a proper next action. What I said in the demo as well is that machine learning models are also always embedded in a business process, and it's very important that we also keep track of that in a way that there's going to be action taken on top of our predictions, and the downstream business processes can also fail. So that will impact the ROI that we will make with our machine learning use cases. And our model can be working perfectly, but if we take the wrong actions or the process later failed, or for instance here, if we go back to the customer lifetime value, if we don't do the proper campaigns, or there are mistakes happening there, we're not going to be achieving the same ROI, and it's going to look like our machine learning model is failing, where it's technically it's the business process failing. And it's very important for us data scientists that we can distinguish between both, so that if business comes to us, or ideally we see it in our dashboard, that things are not as they're supposed to be, that we can instantly resolve them and that we can be more proactive regarding that. And this is actually also a very, very common failure of machine learning model failure in production. Another one is a typical where we have some training serving skew. Maybe during the test setup or during training, we did some overfitting, or maybe there was some leakage, or the typical ways that also when we gather our training data and how the data is created in production might be a little bit different than when we deploy the machine learning model. We see these discrete jumps in performance that are caused basically by all of these potentially modeling or data science mistakes. And this is also something that we can instantly capture if we estimate performance and resolve accordingly. And because machine learning models are trained on historical data, deployed into the real world and making prediction on today's data, and because today's data might be very different because the world is constantly changing, the patterns and assumptions that were true during training might not always hold in production. And that's why most of the machine learning models today are actually just bound to deteriorate. It's a natural process. And that is typically what we see here for a classification model, but that would mean that over time, the performance gradually deteriorate. For a regression use case, that would mean that the error or the loss would go up over time. And it's important to create visibility on that so that we can know what to do. And often we as data scientists can also decide to not prioritize fixing or rebuilding a machine learning model and let it slowly deteriorate, because there's a lot of things on our plate already, and maybe something our new use case is a more valuable use of our time. But at least by having the visibility and by communicating about it, we show that we know and we show that we understand our systems, and this builds trust in what we're doing in our data science departments. And that's it with regard to the more data science and theoretical part of this demonstration. Before I delve into giving a little bit more of an overview of how we can integrate NannyML inside of your production environment, I'm quickly going to chill that today we're launching on Product Hunt, and it would be great if you could quickly scan this QR code or go to the Product Hunt website and support us there. We're fully open source, and it's always nice to get some reach and for people to try us out and to get to know us, to get to know more about us. That's also why we basically organized this webinar today, to kind of create some momentum and to get some visibility, because we recently launched regression, released regression support, and also command line interface, and a possibility to Dockerize containers. And we also iterated a lot on our interface with a lot of users of NannyML, and it would be great if we can potentially get some support there. So head over there and be sure to leave a comment or give some feedback. Okay, and that brings us to this last part, this webinar, which is showing how we can integrate NannyML in production. Like Wojtek said, I'm more of a hacker type of data scientist and not so much engineering like. I'm always afraid from the command line, but that is exactly what I'm going to show today. So we have prepared, maybe I'll put this, because we have on NannyML GitHub, this is our NannyML GitHub, where we just have our open source package. We also, in our organization, have a examples repository where all of these integrations that we do, we store them there, and you can have a look at them. And then there's a configuration file that you can tweak and make it work for your specific use case. And today we're going to look at the regression example and all of the documentation to run this here and how to get your Docker containers locally explained here. And I'm just quickly going to walk you through on how to do that. So of course, you'll have to clone that repository locally. And I'm already in that repository. And the first thing that we're going to have a look at is what we're exactly going to Docker compose. So Docker compose is a way to orchestrate containers. So I can have a quick look at that file, at the YAML file, what's inside. This is already prepared by us. You don't have to really change anything in here. It's basically saying that there is 3 containers that are going to work together, one of which is the NannyML container. And that is just a command line interface that uses the NannyML open source library, and that is containerized. And then we have a Grafana container and a metric store container. After we run NannyML, whether it's scheduled or ad hoc, it's gonna store all of the outputs in a Postgres database, but that can be basically any type of database that you want. And then that can be fed into Grafana, and there is some template dashboards out of the box that we've provided. There is, of course, one thing, what I said before, if you want to set up a monitoring system, there's a little bit of configuration to do. And we can do that in NannyML itself. There's a configuration file and NannyML or a NannyML engineering joke. We can have a look at that as well. And this is all the configuration that we have to specify in here. It's not that much, but I'll quickly walk you through it. So we basically have to specify where our reference data is stored, where our analysis data is stored, and that can be a local file system, cloud storage, or a database, and also where if there is ground truth, where it's going to be populated as well. Then our database, which is the other Docker container, and right now this is already pre-configured. we have to specify what type of use case we're working on. Here we're doing regression. We also have to say on which granularity we want to chunk. We decided to do here daily. We have to do some column mapping and being verbose about which are the features that are specifically going inside of this model. And then also the time dimension and some of the other stuff that we specified inside of our library interface when we were still in Jupyter Notebook. And then that should be it. And we can just do Docker compose up, and that should be running. So it's creating the containers. Not a little bit. This is just some logging for setting up Grafana. And then slowly we should see NannyML boot up. And we see that here NannyML is going to execute, and it's basically running all of the things that we had run before inside of the notebook. And then in this case, we're doing some univariate drift detection, also the data reconstruction with multi-multivariate. We're running the performance calculator. We're doing direct loss estimation, and we see that the NannyML container has successfully exited. And that means that we should be able to go to our dashboards and refresh this. This was the previous run. I'll have to log in, which is NannyML. And then we can see here that we have our dashboards. One is with regards to performance, and the other one is with regards to drift. And we basically get the same type of view, but in our usual Asana setup. There's a lot of drift here because we chunked on a day. And these are also just out-of-the-box dashboards that don't truly leverage the power of the full library. And then we also have some performance dashboards here where we can see some of the alerts for the real-life performance, and in this case, that's mean absolute error. And that's how you deploy NannyML. I'm gonna quickly show something else as well, because this is just a one-off run, but we can also do NannyML in a scheduled way. Docker compose that. Okay, and then I'm gonna go to the incremental example. All right, and I'm quickly going to show for this example, because here NannyML is scheduled to run every few hours or every few minutes. I'll have to look how we set it up in the configuration file. But again, we can go into that YAML file, and it's more or less the same. The only thing here is that how this is set up and how this storage is set up is that basically there was some folder structure, and every day that data gets dumped and then renamed for every API call. Not exactly sure, but there's a lot of optionality and variability that can be introduced here. But the most important thing is that we are here scheduling indeed NannyML to run every minute, and that means that if we then set this up, we can actually see how NannyML would be used in a real-life use case where there is a prediction service and where there is a constant stream of data going to it. So again, NannyML setting up. It's going to be the same thing, but except having a complete view on our production environment, we'll only see one data point at a time. So we see that here it's writing the results and then sleeping until the next run. So that means that we can go back to our Asana dashboard. This is a new Docker compose, a new container setup. So we'll have to log in again because it's not the same anymore. And then we can go to our dashboards, and we see that we've one data point populated. If I set a refresh on them in a few seconds, you should see the next data point appear. And then we can basically see how NannyML would work on a use case that is being and making predictions live. And there we go. And this is gonna keep going forever until I shut this down. But that was basically it from my part. Let me see if I had some other slides. Yeah, just a quick summary that we discussed: silent model failure, the covariance shift, the concept drift, and the delayed ground truth dimension of what makes monitoring hard. We zoomed into a little bit of the monitoring system and the analytics engine. We had a quick demo in Jupyter Notebook on the customer lifetime value regression use case. We discussed the modes of failure, alert fatigue, and also how only drift to uncertain regions is covariance shift impacting performance. We talked business process failure, training serving skew, and also how all machine learning models are bound to deteriorate. And we also had a quick demo on how to deploy NannyML in production. Maybe something more what we're working on, because we're very excited here at NannyML because we're doing some very cool research. That's also why I get labeled the hacker data scientist, because we have some proper real deep data science expertise at NannyML. And right now we're reaching concept drift. We're making great progress with that. And probably in the next 8 weeks, there's going to be a release where we're integrating concept drift together with our performance estimation algorithms, because today the performance estimation algorithms only take into account covariance shift and not concept drift. But that's going to be solved in the future. And then we can also attribute drops in performance to concept drift, covariance shift, the interaction, and we also quantify the impact of those. And that's going to be something that is really going to solve the ML monitoring problem today. We're also researching segments and how we can have performance on a segment level, and specifically identifying underperforming segments. It might be that overall performance is still the same, but that there's certain segments that cancel each other out, or segments that are more profitable. And if we have less performance there, then that's going to impact our ROI, and that's not something that always is directly visible. And we're always looking for new and fun ways to integrate NannyML. What we discovered is actually by talking to data scientists that when it comes to the MLOps frameworks out there and what's being used, everything is very different. So we decided to build our integrations as our users ask for it. And that's also why I gave the quick demo using Grafana, because that was something that's being asked for. And we can really not make a first best educated guess of what is the most likely thing or most likely ML framework that people today are using, because it's still all fairly immature. So that's why we're asking for our users to bring it to us. So if you're looking to integrate NannyML and you're also happy to talk about it and give us some product feedback, and then we can set up a informal design partnership relationship, where we just help you on board, build the integrations, and in exchange, you can tell us how we can improve the product. And that's it for this webinar. Thank you very much. And I hope we can delve into the questions. See that there's a lot of already being asked. But maybe you can guide the conversation a little bit.
Absolutely. Thanks a lot, William, for this webinar. It was super cool. And now let's indeed delve into the questions. I'm going to start with the ones in Q&A. We have 14 questions, so there's going to be quite a lot. And then we're going to do the chat. So without any further delay, Jean Metz is asking, can you use any model implementation from other libraries such as scikit-learn? I'll be answering these questions for the time being to give William a bit of time to breathe, but William, of course, always feel free to chime in. So yes, one really nice thing about NannyML is that we're fully model agnostic, which means that we don't actually need your model file. We don't need to know your model. We don't need to see your model. We only need to see the data that comes in and the data that comes out. Which means that you can use models from scikit-learn, from LGBM, from XGBoost, from PyTorch, from any library. Like, we really don't care. Even your models can even be manual if else statements, and we can still monitor that. So even mathematical modeling can be monitored by NannyML. Then, sorry for butchering probably most of the names here. Bhumika Lamba is asking, what is the difference? What is the difference between loss and error? So difference is in general not really well specified. The way we look at it is that loss is some form of absolute change in performance, sorry, absolute measure of mistakes or measure of errors. So loss is always unsigned, whereas error can be signed or can be not signed. So you can have just error defined as true prediction minus the predicted prediction, true target minus the prediction, whereas loss would be that absolute. And if something is absolute, we can estimate it, but we cannot really predict a signed error, because predicting signed error would be in a way equal to predicting the target. Hope that answers your question. And then from Luis Guimaraes, how many free parameters are available to the user to fine-tune for the error/outlier detection? So I believe here you're referring to the multivariate drift detection with reconstruction error. And there, currently we support one kind of compressor decompressor, which is PCA, and then you can just tune the amount of variance that the PCA is supposed to capture. So this is just one parameter. We are working on also adding new ways of doing multivariate data drift detection, including putting different compressors in our algorithms, such as autoencoders, and then we will, of course, expose to the user that. But right now, you have just one parameter that kind of regulates the strength of the compression or how lossy the compression is. I should be clicking answer live here. Sorry for not doing that, but you heard the answer. Now from Christophe Leroux, probably. Does NannyML work for all sorts of models, also neural networks and deep learning models? So yes, as I already mentioned, we're completely model agnostic. So whatever model you have, as long as it's supervised learning that does either classification or regression, NannyML will be able to estimate performance. And NannyML drift detection methods, so univariate and multivariate drift detection methods, can work on any kind of problem where you have model inputs. So it can also work on unsupervised learning, graph learning, whatever you have there.
And we also support multi-class, and maybe to chime in as well a little bit. When it comes to very advanced NLP models or to very advanced image models, what you will have to probably do to do univariate data drift detection and to make it understandable is to add some type of semantic layer, where basically your very advanced features are transformed to a little bit more interpretable, because at the end of the day, your data drift is meant to be used as a root cause. And when you use the very advanced NLP models and the embeddings, it's going to be hard also for you to kind of analyze what really is drifting.
Yep.
Go ahead, Wojtek.
Thanks for that. So now from Elias Ortiz, click to answer live. Can we get more info about how data is compressed/decompressed for the multivariate shift, please? Yes. So I think the easiest way to do it actually is I have a slide for the talk that I'm doing from time to time. And I think that the best way to do that is just share the screen now, and I give you very quick overview of how this thing actually works. So you should be seeing my screen right now.
Yeah,
I'm not gonna open the presentation. It's just a very quick idea of how this works. So what we do is we take the original data, then we use a compressor such as PCA or autoencoder to compress the data into latent space. So it has to be anything that learns how to project the data from the original data to latent space, which is lower, has lower dimensionality. So any kind of dimensionality reduction, encoding, or compression technique will work here, as long as it actually learns this compression. Then what we're gonna do is we're gonna inverse this compression. So in autoencoder, it will be the second part of the autoencoder. With PCA, we're just inversing the transform. So we need to have a way to do that. And then we get the data reconstruction in the original space. And what we're going to do later is we then compare the original data and the reconstructed data. And what we get is basically the difference between those. We use just Cartesian difference in the original space. And then we take the mean of that, and that's our reconstruction error. So what we will do there is we will plot this reconstruction error over time. And what happens is that if this reconstruction error increases, it means that the structure of the data that we learned is no longer relevant to the current data, because we will be then transforming and inverse transforming every chunk of the data in our analysis, but we will not be refitting that. We only fit it on the reference data set. So that means the transformer will learn how the data looked in the reference data set. And then if something changes, we will see that this compressor decompressor is no longer performing well. And that's really just high level intuition. If the reconstruction error goes up, it means that the structure of the data is different. If the reconstruction error stays roughly constant, it means that the structure of the data is roughly the same. And if it drops, that's an interesting edge case. It means that the structure of the data has changed again in a way that makes the compressor capture the structure of the data better, which means, for example, if we use PCA, that the data is more linear, or the linear relationships within the data are stronger. So that was a bit more involved answer, but I hope it satisfies you. And then next question from the anonymous attendee. One question I have is that in case we notice the drift in our system, what would be the best way to correct it? It would be great if you could discuss the correction process for both cases. So whether we have covariance drift, covariance shift, or lack of ground truth. So William already covered it briefly, but maybe I'll just give a quick overview of how we do it. So basically, if you have covariance shift, there's basically two options here. One option is to just correct things downstream, because covariance shift means that your model, if you have performance drop due to covariance shift, it means that your model has moved to the areas where your model is not as good at making predictions as in other areas. And this can be due to two reasons. Reason one is that it moved to a region when there was not enough data, so it has not learned to capture the pattern correctly, the actual pattern that we want to capture. In that way, what you should do is you should gather more data in this region, or gather more labels in this region, and try to retrain the model. However, another option is that it moved data moved closer to region when it's just inherently harder to predict the target. Maybe, let's say in classification, it's very close to the class boundary, when there's just a lot of noise and it's impossible to tell whether the class is going to be positive or negative. In that case, retraining will not really help, and it doesn't make sense to spend resources on retraining. So what you should do instead is simply deal with that downstream. So maybe change your business rules, how you actually treat the predictions, maybe take the model down if you need to, or take all the predictions from this region and run it by manual analysts, because simple training will not do. These things are just hard to predict. And if you have concept drift, so the second reason why models can fail, then retraining is the best way to do it. But interestingly, if you have very sudden concept drift, you should not retrain on your entire data set, because the concept that you have in your first part of the data that you trained originally on and the concept that you have currently might be different. And trying to learn both these concepts at once will actually lead to worse performance. So then you should either train only on the recent data, or try to somehow induce this concept drift in the previous data. But that would be going a bit too deep into that. So let's call this question answered and move on. Next question. So in last solution will be to retrain the model with all features. Yes. So we should potentially retrain with all features. Sometimes, as I mentioned, we have to redevelop if there is significant concept drift. And in that case, we need to figure out what features to use again, what data to use, because it's not necessarily a given that we should use everything, because sometimes it will actually hurt our training because data comes from a different distribution, different population. Then we have another question from Christoph. Do all models drift or deteriorate if given enough time? He presumes yes, and Christoph, you are absolutely correct. Models will deteriorate just because everything changes in time. And there is an interesting nuance here, is that if your model performs very well in absolute terms, so let's say that your MSE is very low or your percentage error is close to 0, it means that your model captures most of the information that is needed to really make perfect prediction. And there's less things that can change. The concept will not really change because there's really nothing unseen that can drift, which means that the models that perform well will also tend to be more stable and will still deteriorate, but slower. And the models that are less stable, let's say that you're trying to predict credit scoring based on mobile data, and your ROC AUC for that model is 0.6. So it's barely better than random. It still provides a lot of value because maybe it's the only way you can predict it. But this model, you would expect it to deteriorate very fast, and then monitoring is even more important. Then we have another one from yet another anonymous attendee. I think it's the same actually. So if I'm training my model daily, so to decide if I go with the new trained model or the all trained model, how can we go about it? So what you can do is A/B test it, and the way you could do it is you could deploy in some kind of sandbox environment both models, monitor them with NannyML, and see which of the models actually is expected to perform well. So normally you would do such A/B testing with the ground truth. With NannyML, you can do that A/B testing even without the ground truth, just based on our performance estimation algorithms. And then you'll be able to decide whether the old model is better or the new model is better. Whew. Okay, a few more to go. These questions keep coming, and we're slightly past time, so I'll just go slightly faster. From Ali. Once it is established that the deployed model is not performing well, would NannyML explicitly describe whether performance is due to covariance shift and or concept drift? That's a great question, and this is exactly something we're actually currently researching. So we're researching the attribution between concept drift and covariance shift. We call that root cause analysis because it gives you basically the first step to determine what is the root cause. Right now, NannyML will not do it explicitly, but we would love to chat with you to understand a bit more about the use case, to figure out how we can do it, because that is something that we plan to put in production, honestly, around March. And by then you will have it. Right now, this is something that you have to do as data scientists and ascertain yourself based on things like multivariate, covariate shift, and the performance estimation algorithms. From Randy Sanjaya. Can the alert be produced to send alerts, let's say, to Telegram if the model is trespassing the thresholds? That's another thing we're working on. We honestly did not plan to support Telegram, but that is very interesting to see also Telegram featured here. And that is something that's on our very near-term roadmap. So in the next 2 months, we will start supporting explicit integration with email, with Slack, and potentially adult channels. Honestly, Telegram is quite unlikely to make the cut because we've seen most demand for email and for Slack. But Randy, again, it would be great to talk to see why Telegram is specifically featured here, or maybe that was just an example. And then there's a kind of follow-up also from Randy. In regression type of analysis, how exactly we get the actual Y value beside the prediction to compare with performance? So the magic thing here is that we don't get it and we estimate it. And we estimate it based on how we can predict the uncertainty of the model by fitting yet another model that would try to predict the absolute error or loss for every single data point. And then we just average it across given chunk of data or your analysis period, and that's how we get the number. So we can do it without getting the actual Y value, and this is the real magic here. Then from Jean Metz, what cloud environments are supported as input data sources? So for the CLI, we are cloud agnostic because you just deploy your CLI wherever you want, and then you can take your data from Azure, from GCP, from even like local clouds, from anything you want. But as I already mentioned, we're working on integrations now, and we're planning to add very simple, easy support, not only for the CLI, but to actually get the data directly from your cloud sources. And there we plan to support Azure, AWS, and potentially GCP. Then another question from Randy. If you guys already know about MLflow, yes, we do. How is the position of NannyML exactly? So we position ourselves as clearly post-production tool. So I think MLflow is really great for design experiment tracking and helping you deploy your model. It's really the go-to tool for that. And I think it's also great that it has a very strong open source component. But it doesn't really do much when it comes to post-deployment stuff, and that's where we come in. So we see ourselves as fully complementary with MLflow. How to create alerts from inside NannyML Docker? Julian, can you actually just add a link to the documentation there? I think this is the best way to answer this question. But if you have something that you want to say live, go ahead.
I'll say a quick answer there, because right now as you could see in the containers, there wasn't an alerting container spun up. You can do that, but right now with this example, you could set them up in Grafana. They also have some support for alerting, and there's also tools that you can plug easily in yourself to get alerts. And that is the beauty of open source. It's building all together on top of that. So if you need that fast, that would be the way to do it.
Okay, and Julian, if you can please put the link to documentation there.
Yeah.
All right, only 4 more questions to go. So stay with us for a few more minutes. From Jerun, how are the thresholds for performance reports set? Can we also make them dynamic? So yes, right now the questions, the thresholds are set using kind of smart defaults, and they are basically just, if I remember correctly, 3 standard deviations of your performance on your reference set. It could be 2, but I think it's 3. And this is something that you can adjust deep in the code. So this is something that right now we kind of went MVP style. You can adjust it, but you need to go a bit deeper in the library to do it. There is no top level interface for that. This is something that we're planning to add soon, but you can already do it if this is something that is necessary for you. Yet another question from Jean Metz. So for the real big influx of data, say 5 million of data points per second, that is really big. How does NannyML perform? What are basic infra requirements for this scenario? Well, honest answer, it doesn't perform. It is not optimized for such a huge streams of data. What you could do is that if your model can actually make predictions that fast, which is honestly really impressive, if you can just basically have the same setup just for monitoring, then NannyML should be able to handle that. Big data is, again, a huge topic for us and something that we'll be working on in the next 8 weeks. So again, it would be great to talk. What we plan to support is to support partial fit for all the functions we have, so you don't have to keep all your data in memory for reference fitting, making sure that you can easily store fitted methods and then just call them, and not run the entire analysis period at once, which is unfortunately right now how it is. So right now, I would say don't even try, and give it a try. If you actually have 5 million of data points per second, give it a try in 8 weeks from now. So at the end of January, we will have support for big data. I'm not sure if 5 million of data point per second kind of data, but definitely we can handle good few terabytes a day. And then a last question, first one from Ali. In case of univariate covariate shift, can NannyML rank the features from the most drifted affected to least? The idea is to focus our model retraining attention on the top features that are degrading the model performance most. Great question, Ali. So yes, we can do it. Right now, we have extremely basic ranker feature that only supports the number of alerts. And actually by the end of this week, we are releasing a slightly more advanced ranker feature when we will not only look at the number of alerts, but also the correlation or the correlation between the drifted features and the change in performance. So you can actually kind of figure out what is the potential cause of it. And then if you just want to look at what is the most drifted, we return a pandas data frame with the results file for everything that we run. So you can then just rank there and you will see what has the strongest drift, either in terms of the actual value for the univariate shift, let's say the distance value, or the statistic in terms of KS test, or p-values for our statistical test. So we have right now, I think in total, 6 different ways to do univariate covariate shift detection, 3 for categorical, 3 for continuous. And there, when you get the results, you can always just rank. And then from Jean Metz, does it support multi-label classification? Jean, you're the first person that has ever asked for multi-label classification. This is something that actually wouldn't take that much time, but nobody wanted it. So right now we support multi-class and binary. There is no explicit support for multi-label, but if you're willing to go through a bit of manual data processing, you can always transform multi-label classification into multiple binary classification problems and monitor it like that, because that's what just multi-label is. Yeah, too much data to specific use cases, but would really love to talk because these things are super interesting from our perspective. All right, and with that, I think we're ready. Just quick check in the chat. We'll be sharing the notebook. Well, I'll leave that question to you.
Yes, we will.
And
also probably the recording as well of this session.
Yeah. So that I want to thank everyone, especially William, who was our great presenter here, and all the attendees, especially 30 people who stuck up until now. And we'll be seeing you next time.
Wojtek, also thank you.
Anytime. Anytime, buddy.
See you next time.